Yes, your presentation can be in 10 minutes. Thank you.
Okay, thanks, Professor Wang. And let me go first. And I'd also like to thank Lin and John because I received this lovely conference package, and I do like it. Thank you. And thanks everyone. And I'd like to have a brief introduction about myself. And my name is Maomao, and I'm currently a postdoctoral researcher at the University of Oxford in the Department of Engineering Science. And today I'm going to be talking about my research, which is the classification and categorization of the smart meat data using the interpretable feature extraction and feature-based clustering. First of all, I'd like to have a brief introduction about my research. These days, both today's buildings and the electric grid are undergoing some changes. For the buildings specifically, in the buildings nowadays, we've installed a lot of high-tech devices like the smart sensors, the smart meter, and the energy management system, and the local area networks. And all of these devices are generating a large volume of the data. So that today's buildings and urban are becoming both the energy intensive and the data intensive. Buildings are not standing alone, and they are actually a part of the electric grids. They are the demand side of the grid. And at the supply side, we know the electricity will go through the generation, high voltage transmission, and low voltage distribution. And nowadays, both at the demand side and the supply side are undergoing some changes. At the demand side, we have the on-site PV systems and the electric vehicles. And at the supply side, we have the wind turbines and the solar energy and the energy storage systems. So today's grids, electric grids, are facing the power imbalance issue because of these new technologies. So what specifically are the power imbalance issue? I'd like to give two examples here. The first one is called the duck curve, and this figure shows the daily net demand trend in California on the 18th of April this year. And the green line here is the demand at the demand side, and the purple line here is the net demand, which simply use the demand minus the generated renewable energies, including the wind energy and the solar energy. Because this curve here is like a duck, so we call it the duck curve. And so what's the problem with the duck curve, right? The first one is it might have the risk of the overgeneration issue here. Another one is the steep ramps. And basically during the 3 hours from the 4 o'clock p.m. to the 7 o'clock p.m., the utilities need to provide the power about 16,000 megawatts, and it's a challenge for them. Another case is the power outages across the Texas caused by the windstorm in the February this year as well. And the colors here denote the outage scale, and we can see a lot of the larger portion of the places are suffering from the power outage. So how can the buildings help the duck fly and make the duck less saggy and help and the building? How can the building help to avoid and relieve the rolling blackouts? Before answer that question, we need to understand why buildings, right? And because buildings account for around the 40% of the total energy use and 36% of the greenhouse gases globally. So to solve this problem, to address this issue, buildings need to be both the energy efficient and grid interactive for the demand side management. So what's the benefits? They can help us improve the penetration of the renewables and improve the reliability of the electric grids, and it can help to reduce the CO2, and also it can help the both the end users and the utility to save money. So what's my research question and objective here? You know, in the UK, 50% of the households have been equipped with the smart meter, and the utilities have a large volumes of the data. But how can we extract the actionable information and knowledge from this data? And then we can improve the demand-side management at a distribution network level. And specifically here in our study, we addressed two tasks. The first one is load pattern categorization. You know, conventionally, we classify the buildings based on the building types, whether the building is industrial buildings, commercial buildings, or domestic buildings. And or we can classify buildings based on the energy consumption level, like the buildings with high energy consumption and the buildings with low energy consumption. And the idea here, how about we classify the buildings based on the pattern of the smart meter data? And now the second task is in the UK, some households install the PVs without permission from the government. So that is detrimental for the network reliability. So here we also want to identify the PV unreported PV installations based on the smart meter data. And for the clustering, you know, the crucial, as this guy said, the crucial problem for the classificator is not the algorithm, it is linear or non-linear, but the selection of the well-discriminating features. And in addition, the features can contribute to the understanding of the properties of the smart meter data. So how we can extract the interpretable features? These pictures show we developed the method to extraction two kind of features. One is the global feature, and here we can see we can get the feature like the maximum value, the minimum value, the range, and the longest period of the successive increase, and the longest subsequence above mean. And this is quite conventional global feature. And we also extract the peak period features based on the sex volts, which is the symbolic representation. As you can see, we can transfer the raw data into letters, the alphabetic letters. So after do this transformation, we can easily find where are the peak periods are and the starting time of the period, peak period, and the duration, the upward slope here and the downward slope here. And we developed a Python package which is called IFO, and which is short for the interpretable feature extraction of electricity loads. And the pronunciation is quite like the Eiffel Tower in Paris. And you can easily install our package if you are using Python. And the stage 2 is after we get in the interpretable features, we can do the clustering using the k-means. One of the critical questions about the k-means is how we can determine the clusters. And here we're going to use the silhouette score and the collectivity score help us to determine the clusters number. And before that, because we might have 20 principal components, but not all of them are equally important. To reduce the dimensionality of the data, so we're going to use the PCA to reduce the dimensionality of the data. And we didn't stop at the clustering, and we will move forward. We want to see what does the clustering results mean. So we do the post-clustering compositional analysis. Basically, there are two. Basically, there are two indexes. One is the variability based on the entropy concept. The another one is the compositional change. For example, if we have like two stones, but we want to quantify the composition differences between these two stones, and the same here the same idea. We want to use the Archson distance to quantify the differences between two households. So here is the results and the discussion about the work. We collected the data, the smart meter data, from around 760 British households, and the data temporal granularity is 30 minutes, and the data is 1 hour, 1 year long. This picture shows the results.
Dr. Hu, excuse me, Dr. Hu, can you speed up? Sorry, yeah.
Okay,
yeah.
Okay,
Time
only
is
like
very
two.
tight. Thank you.
Yeah, thanks. And the dimensionality help us to reduce the dimension, and the k-means help us to classify the data of both the non-PV houses and PV houses. This is the variability analysis based on the entropy, and here we can see the y-axis is the household number, and for different houses we can see they have different cluster membership. And for example, for the household 60 and the household 450, the household 60 it has a high variability because it has 5 different memberships. And compared the however, for the 450, it only has 3 different clusters. And for the compositional change, basically you can see this picture shows the composition, the membership of the buildings through the whole year, and here y-axis here is compositional change based on the Archison distance. We can compare the difference between different day of the week and month of the year, and the same case for the non-PV house 450 with a low variability. Yes, I'm gonna stop here, and we can discuss the questions maybe later in the end.
Yeah.
Thank you.
Okay. Thank you, Dr. Hu. Yes. Thank you. Very nice presentation. Thank you. Okay. So